Okay, so I'm going to talk to you about how we can change the form of a sum of trig functions, like the solutions that we see for the simple harmonic motion case, to one single trig function, which ends up having a phase shift and gives us more information about physically what that solution means. So we saw that for simple harmonic motion, we get this differential equation that looks like x double prime plus some constant times x equals 0. And that has a solution that looks like sines and cosines, where these coefficients here, a and b, come from initial conditions in the problem. So as is, this solution can be plotted if we use some graphing calculator or some like plotting program, or if you really want to plug in a bunch of t-values and calculate what x is, you could plot it that way. But there is another form that we can get this solution to look like, so that we can talk about or easily pick off information such as what the amplitude of our solution is, what the period looks like, or what the period is, and things like the frequency. So what we want is, our goal is to get a solution of the form d cosine omega naught t minus phi. And we can see from this that this is something that's easier to plot. We just have a cosine term. We have some amplitude that's very clear. There's a d that tells us that's the amplitude. We can rewrite this a little bit even more to figure out where to draw my curve exactly. So if I pull out a factor of omega, I can see that my t value is basically shifted by phi over omega naught, which tells us that if I just looked at d cosine omega naught t, that would look something like this. So this is my d cosine omega naught t, but with that phase shift now, we can see that this is telling us, okay, we're actually starting maybe over here, and my solution actually looks something like that, where it's shifted a bit, and this would be d cosine omega naught t minus phi, and that shift from our t equals 0 to where our cosine curve would start is phi over omega naught. So how do we actually calculate, now my cat's saying hi, okay. Thank you, cat, for turning off my video. But so how do we actually get it into that form? So there's another thing that we might want to think about. So if we have, let's say we have a vector, and our vector is a comma b. Fermi does not like differential equations. So we can draw that vector. We know that that tells us how far over and how far up to go. So it goes up to the point a comma b. So the length of that vector, I'm going to say is d, And we know that D can relate to A and B by using just Pythagorean theorem here. So D ends up being the square root of A squared plus B squared. However, we also know that we can take something that's written in terms of these x and y coordinates. So A and B we can think of as being in like x and y coordinates, just for the purpose of this. And we can think about how to put that in terms of polar coordinates. So change x and y to go to polar coordinates. So the way that we can do that is we know that A can be rewritten as, I'm going to call it little a here, cosine of some angle, where this is my angle that my vector is taking, and B can be rewritten as B sine of that angle. So if I look back at my solution, I can think of my my coefficients as points on this sort of coordinate system. So this is my original solution. I could think of points on this coordinate system where now instead of, that point being at A and B, I want to rethink about it in terms of what that angle of that vector is. So I'm going to change my coordinates here, and I'm going to say, well, big A is going to be little a cosine phi. And then I still have cosine omega t, and big B is going to be little b sine phi sine omega t. So I messed this up again. That's okay. We're going to backtrack 1 second. So I made a mistake here. These coefficients in front. So when we put it in sort of our polar coordinate system, we have it in terms of the length of the vector, which is d, we said, and that angle that our vector takes. So I'm just going to go back and erase those other coordinates I had. I'm looking at my notes and I've like switched some things around, so I just wrote down the wrong thing there. But so here we can now, I'm going to put those D's in, and we see that we have the same coefficient out in front, which we didn't have before when we had the big A and the big B. And then I have this multiplication of trig, which looks like I'm making it more complicated here. But one thing that we can use is this trig identity. So this trig identity that I'm going to use is that cosine of x1 minus x2, where they're just some, whatever numbers, is cosine x1 times cosine x2 plus sine x1 sine x2. So I can see that my equation is now of that form where x1 is, I'm going to make it omega t because I want that one to be first, but it doesn't matter. You end up getting the same thing. But since I know I'm looking for a particular form right now, that's what I'm going to do. And x2 is phi. So that tells me that I can rewrite this as d, and then this tells me that it's cosine omega t minus phi. Okay, so that's how we can get that form, but now we need to know, so how do we find D and phi? So D, I'm gonna say, well, we actually already found D. We said that the length of the vector is just going to be the square root of the sum of the squares. So D is going to take those two coefficients that we found by initial conditions, and we're just going to use the distance formula on them. Now, phi here is a little bit tricky. So first, I'm going to look at this simple case where my A and B are in this first coordinate system, or in this first quadrant, I mean. So if I think about this triangle and think about SOHCAHTOA, we can see that, there we go. We can see that the tangent of phi is going to be opposite, which is B, over adjacent, which is A. So B over A. And that means that phi is arctan B over A. And that doesn't seem so tricky right now. That seems pretty straightforward. However, we have to be careful. And the reason for that is just because of how the arctan function works and what quadrant we're in. So in this case, we have A is greater than 0. And basically, if you know A is greater than 0, you know that your phi angle is just going to be arctan B over A. But there are two more cases that we do want to check for, and I'll summarize them for you. Okay, so what if we have coefficients that make our vector over in this quadrant? Okay, so we're still looking for phi, but we have an issue with the quadrant that we're in. So one thing I'm going to do is I'm going to extend this out so that now I have a perfectly straight line. And the way I'm going to think about this right here, this angle phi, or wow, psi, I'm going to think about psi and say, well, it's my angle phi, so I'm all the way over here, but I'm going to subtract off pi from it, and then I'll be down here. And you can tell that if I subtract off pi from this vector, that moves my vector all the way down here. All right, so what does that mean? So that means that we can take, we can think about what this psi is going to be, because that psi is within our arctan function. If you, just as a reminder of what arctan looks like. So this is going to be, I'll say just x. Arctan ends up looking like this. So this is arctan of x. So it goes between pi over 2 and minus pi over 2. So whenever we're in this area here, so whenever we're in this quadrant and this quadrant, we're in that pi over 2 to minus pi over 2, and we don't have to worry about doing anything fancy with it. So that's why we want to extend and look at what happens to that angle over there. And then we're going to add pi to that, and that should give us what phi is. So this angle psi, well, psi is just going to be arctan of b over a. We can see that this sort of angle here would be the same thing as if I mirrored it up. So just like in our previous case where this was arctan b over a, we still have arctan b over a. So that means that phi is going to be psi plus pi. Now I'm saying a bunch of i's, it's all rhyming here. And that's going to be arctan b over a plus pi. Okay, so that's case 2. And lastly, case 3. So that's going to be when we are down here. So that's my a comma b. And in this case, we're going to do something really similar. We're going to extend this line up. So I have kind of this minus a comma minus b here. And I'm going to look at this angle psi in this case. And we can see that this psi is this phi that we care about. That's our unknown. And then I'm going to add pi to it. So let me do that in another color so you can see. So we're going to add pi to that. So we have this relationship now that psi equals phi and then plus pi. And we know in this quadrant what psi is. Psi is arctan b over a. So this tells me ultimately that when I'm in that quadrant, phi is arctan b over a minus pi. So just to summarize what that means, so my phi, that phase shift, is going to depend on the coefficients of my two trig functions, and it's going to depend in such a way where if a is greater than 0, so if I'm in quadrant 2, or in quadrant 1, then I just have arctan b over a. If a is less than 0 and b is less than 0, so that was our second case where we were over here. So if I'm in quadrant 2 now, so the first case, actually, since we just care about a, it's quadrant 1 or 4. So in quadrant 2, we have arctan b over a plus pi. And if a is less than 0, but b is greater than 0, so that was that last case where we're in quadrant 3, then I have arctan b over a minus pi. So those are the 3 different cases. Let's maybe do a quick example. So let's say, okay. So let's say we have a differential equation that looks like this. Example, 4y double prime plus 169y equals 0. Or we can rewrite that as 42.25y equals 0. So in this case, we know first that omega naught is the square root of what I have here. So this is going to be the square root of 42.25y. So I already know what that is. Nope, no y there. Sorry. And that's going to be 6.5. So our solution, since we can see that it is simple harmonic motion, is going to be A cosine 6.5 t plus sine plus B sine 6.5 t. So for this, we're going to have initial conditions. Y of 0 equals 0.1. Y prime of 0 equals 1.3. This is in meters, and this is in meters per second. So if we were to solve this initial value problem, we end up getting that our coefficients are 0.1 cosine 6.5t plus 0.2 sine 6.5t. So now that we have all of our values in this equation, we want to rewrite it. So we find we want it in the form y of t equals d cosine omega naught t minus phi. So d here, we said, is going to be the square root of the sums of the squares of my coefficients. Okay, and that value is something that's kind of ugly. I'm gonna round it maybe to 0.22. We'll just leave it at that, 0.22 meters. Now looking at my coefficients here, I can see that this first one is positive and the second one is positive. So in quadrant 1. So that means that phi is going to be just arc tan 0.2 over 0.1. And that is going to be 1.1071. It's not necessary to be that long. Let's just say that it's going to be 1.1. So we can see that our solution is, our final solution is 0.22 cosine, our omega naught, which we found at the beginning, 6.5 t minus 1.1. So just to do one more quick example, let's say our initial conditions gave us, I'm going to pick something kind of similar to what we had, but I'm going to change one of the signs. So that we're in a different quadrant. So let's say our initial conditions gave us, I don't know, minus 0.1 cosine 6.5 plus 0.2 sine 6.5 t. So first we notice that d is the same. Doesn't matter. The numbers are the same when you square them. The signs in front of them don't matter. The length of that vector doesn't matter which quadrant it's in. The length's going to be the same. Hi. Now my other cat's on. Hi, sweetie. Okay, so next we have to think, so which quadrant am I in now? So if A is negative and B is positive, that means I'm over here. So in this case, we saw that when we are in that quadrant, when A is negative, and B is positive, so when we're in this case here, we end up adding our pi. So my phi equals arctan, which was arctan 0.2 divided by 0.1 and plus pi. And I'm not sure exactly what that is, but the arctan is the same. So it's, I guess, 1.1 plus 3. I'll say 3.1 right now. So this is going to be 4.1. And solution looks like y of t equals our d, which was 0.22 cosine 6.5 t minus 4.1. And that's it. So hopefully this was helpful and made sense. I may have a small mistake somewhere in there, getting distracted by cats and stuff. But if there are any other questions, please let me know, and I can elaborate